Welcome. In this second last video we look at Unit 21 and Unit 22. 21 is about Green's theorem and 22 is about a few derivatives, the curl, the divergence, and the last integration, which is the flux integral. So let's get started with the theorem. It's a very exciting theorem and it's all in the plane. So we are not in space, we are in the two-dimensional plane, and we are given a region. It's green because of green and has a red boundary. The boundary curve is oriented so that the region is to the left. Let me just write that down. It's to the left. And then there is a relation between the double integral of the curl. We have seen the curl already, qx minus py. It's a scalar function which measures the vorticity of the field, and we have also the line integral along the boundary. So it's a fantastic theorem. It's the second generalization of the fundamental theorem of calculus to higher dimensions, and ends also all the theorems in 2 dimensions. So next Thursday we will then look at Stokes' theorem and divergence theorem, which are theorems in space. But today we are all in the plane, at least for Unit 21. So this is this theorem. I will explain a little bit in class why this is reasonable. But there are 2 special cases which you should consider, and one of them is when the curl is 0. It's a very important case. If the curl is 0, that's this Clairaut condition which we have seen last time. If the curl is 0, then it's actually a gradient field, at least if the function is defined everywhere. So there is a little bit of technical condition here, which we discuss also in class a little bit more, but you can ignore that for the most. And so if the curl is 0, then you have a gradient field, and the line integral is 0 also by the fundamental theorem of line integrals. So that's kind of a special case. Both sides are 0. Another special case, very important case, is if the vector field has curl 1 everywhere. That's a very important case because it allows us to compute the area of a region. And that's also the base for the planimeter, which I will show, an analog computer, which I show you at the very end. So this is realized by some functions. Popular functions are 0x, most simple one, or minus yx half. So both of these vector fields have curl 1. And so they can be used to compute the area of regions just by integrating along the boundary. And you will see that here in the 4th section. We will compute the area of the ellipse using this method. Before we do that, let me just illustrate how convenient this Green's theorem is to compute some line integrals. So in this case we have an insane vector field. It's given here to the right, complicated vector field. And we ask you to compute the line integral along the boundary of this dog-shaped figure, which you see here. And that would be a very complicated line integral, completely impossible to do for several reasons, because of complexity, because of functions which are impossible to integrate. So we need a theorem. But fortunately with Green's theorem, this is very, very simple. If you look at the curl of f, so if you look at the curl of this vector field, this is qx. Let me just write this down, pq. And that's just minus 1. So in this case, it's constructed as such, the vector field is actually quite convenient. It just has curl constant minus 1. So the answer can now be written down immediately using Green's theorem. So that's just the integral of the region inside minus 1 dA. And if you take that minus 1, that is just minus 1 times the area. So this is minus 28. This is a typical problem which is impossible to do without Green's theorem, but quite easily done using the integral theorem. This is a very important prototype problem, the area of an ellipse. It would need, and that's what is in the movie done, you need trig substitution, and so it's quite painful to do that. But using Green's theorem, it's actually quite convenient. So what we do is we take the vector field f is equal to 0x, which has curl 1. And then we compute the line integral instead. So the curve, which is a equals to b sin t, so we have to do is 0, and just x is equal to t, and the velocity, which is minus b sin t, and equals to dt. So we have replaced that double integral using Green's theorem. We have replaced it with a line integral. You can compute area quite conveniently using Green's theorem. And finally, that's actually the mathematical foundation for an analog computer called planimeter, and you are just moving along the curve. So if you have a curve, you move along, and then what happens is there is a wheel turning, and that wheel actually measures a line integral. And that is designed in such a way that the area is proportional to that wheel motion. And so the total amount of area can then be read off here. These analog computers are coming back, for example, in the form of quantum computers, which are some sort of analog computers. So that's about unit 21, this integral theorem. Let's move to unit 22, where we introduce also three-dimensional curl, we introduce the divergence, and we introduce also an integration, the flux integral. Let's get started with the two-dimensional curl. That's the curl which enters the Green's theorem, qx minus py. Green's theorem really gives you the foundation, what it means. So if you look at the situation like this, where we have a building and wind going, this is actually the vector field 0x, which we have used for computing the area. This vector field 0x has a shear, so it's getting bigger and bigger as further away you go from the wall. And if you take a leaf and you let it go, what happens, and it goes around, what happens, it is getting pushed here more. The motion produces energy, and that wheel will turn around. It's this dust devil effect. A little bit more complicated things become when you are going into 3 dimensions, and the curl is defined in a similar way than in 2 dimensions as the cross product of this nabla with the vector field. So that's a kind of, if you don't like this, you can just take this as the definition here. So it has as the third component the qx minus py, which you know, and a very important special case to see what is going on is this vector field. This is my favorite vector field to visualize this. It's this minus yx1 vector field, where you have this tornado vector field where you are kind of going up along a spiral. So this is measuring along which axis the vector field rotates, and also the length of the vector tells you how strong this rotation is. So that's the 3-dimensional curl. It's always visualized using paddle wheels, and I brought a couple of them here. So here, for example, that's a cool one. This paddle wheel is turning around. It's a very interesting problem. Why does this turn around? But that's the picture. So what you are doing is, if you want to see in which direction the curl is, so you take that, put the paddle wheel into the vector field and turn it around, and when it turns maximal, when the rotation is maximally counterclockwise, that's the direction of the curl. Now, we also have the notion of divergence. That's kind of needed then later in the last theorem, which is again a scalar. So this is a notion which measures the expansion of the vector field. And then we will verify in class these 2 identities, these 2 important identities. The first identity tells you that the curl of the gradient is 0, and the second identity tells you that the divergence of the curl is 0. So this is straightforward, uses just Clairaut's theorem. The last thing we are going to look at and also compute in examples is the flux of a vector field through a surface. And you have a vector field going through the surface. So it's like a membrane. And when you have this membrane and you want to see, for example, how much blood goes through this membrane, then what you do is you look at this little element here, RU du cross RV dV, which is a small, so it tells you how much of the fluid goes through the surface in unit time. So if we look at the examples, and here on this diagram I show you the overview of all possible integrals. So these are all integrals which appear in multivariable calculus. So of course in one dimension we have the single variable integral, in 2 dimensions we have the line integral and the double integral. And then in 3 dimensions we have the line integral, the flux integral, and the triple integral. And so we are ready. We have all the things together to next time conclude everything with the Stokes theorem and the divergence theorem.